Welcome to our presentation on instrumental variables and the generalized method of moments. This session will provide a practical guide to estimation and diagnostics for dealing with endogeneity, a pervasive challenge in econometrics. As famously quoted, endogeneity is the bane of the OLS estimator. IV and GMM are the antidotes. This statement perfectly encapsulates why these methods are crucial for obtaining reliable causal inferences. For instance, consider estimating the effect of education on wages. An unobserved factor like ability could bias our results, leading to endogeneity. We'll explore how IV and GMM offer robust solutions to such problems. To begin, let's first understand precisely why the standard ordinary least squares estimator often falls short. The core problem we're addressing is endogeneity, which fundamentally means that a regressor, x, in our model, is correlated with the error term, u. Mathematically, this violates a key OLS assumption, as the covariance between x and u is not zero. When this occurs, our ordinary least squares estimators become both biased and inconsistent. This is a critical issue because it implies that even with an infinite amount of data, our estimates will not converge to the true population parameters, rendering our model unreliable. This problematic correlation can arise from a few common sources. Firstly, there's simultaneous causality, where x influences y, and y, in turn, influences x, creating a feedback loop. Secondly, omitted variable bias occurs when we fail to include a relevant variable that is correlated with both our regressor and the dependent variable. Lastly, measurement error in our independent variable can also introduce this unwanted correlation with the error term. To truly fix endogeneity, simply gathering more data isn't enough. We need a structural change in our estimation approach, such as using instrumental variables. This decision map provides a systematic approach for selecting the most appropriate econometric estimator, crucial for obtaining reliable results. We begin by asking the fundamental question: is the covariance between your regressor x and the error term, u, equal to 0? This is the core test for endogeneity. If the answer is yes, meaning there's no endogeneity, then ordinary least squares, or OLS, is the best linear unbiased estimator and your ideal choice. However, if the answer is no, indicating that endogeneity is present, you must employ an instrumental variable, or IV, technique. Once an IV approach is deemed necessary, the next step is to examine the properties of your error terms. If the errors are homoskedastic, meaning their variance is constant, then two-stage least squares, or TSLS, is the appropriate method. But if the errors are heteroskedastic or serially correlated, TSLS is no longer efficient. In such cases, the Generalized Method of Moments, or GMM, is the superior choice, as it provides robust standard errors by accounting for these complex error structures. This hierarchy reflects a progression: OLS as a baseline, TSLS to fix endogeneity, and GMM to address endogeneity while also providing robust inference for challenging error structures. The TSLS method uses an instrumental variable, z, to solve endogeneity. Imagine z as a filter. It processes the endogenous variable x, producing x hat, a fitted value that is uncorrelated with the error term, thereby allowing for consistent estimates. For z to be a valid instrument, it must meet two critical conditions. First, relevance. Z must be sufficiently correlated with x, meaning it must explain x. Second, exogeneity. Z must be uncorrelated with the error term u. This embodies the golden rule. A valid instrument impacts the outcome only through the regressor, never directly. For example, in studying schooling's effect on wages, proximity to a college can be an instrument. It's relevant by influencing schooling, and exogenous if it doesn't directly affect wages beyond education. The resulting instrumental variable estimator addresses this challenge. While powerful, TSLS relies on specific error structure assumptions, leading us to more advanced solutions. The Generalized Method of Moments, or GMM, is an advanced estimator that builds upon two-stage least squares, offering a more flexible approach to endogeneity. At its core, GMM aims to minimize an objective function, denoted as J, which is a quadratic form of the sample moment conditions. These moment conditions, represented by m of beta, are derived from the fundamental exogeneity assumption that our instrumental variables are uncorrelated with the error term, meaning the expected value of z prime u is 0. The weighting matrix, W, is crucial here. It intelligently prioritizes different moment conditions to ensure we obtain the most efficient estimates possible. The key advantage of GMM over TSLS lies in its robustness. While TSLS assumes homoskedastic, or well-behaved, errors, GMM relaxes this stringent assumption. This makes GMM particularly efficient and suitable when we encounter heteroskedasticity or serial correlation in our errors. It achieves robust inference by employing specific weighting matrices, such as the White or Newey-West matrices, which are designed to handle HAC errors. One important alternative to TSLS and GMM is LIML, the Limited Information Maximum Likelihood Estimator. This method works by maximizing the concentrated likelihood function. LIML is particularly valuable when you suspect your instrumental variables are weak. In these situations, LIML often provides less biased estimates than TSLS, especially in finite samples, making it a robust choice when instrument strength is a concern. Another key concept is the family of K-class estimators. This represents a general framework for instrumental variable estimators, defined by the minimization problem shown on the slide. What's fascinating about this family is how it unifies various estimators under one umbrella. For instance, when the scalar k equals 0, it simplifies to the ordinary least squares estimator, and when k equals 1, it becomes the two-stage least squares estimator. LIML itself is also a member of this broad family, where the value of k is estimated directly from your data. This slide provides a practical guide on how to navigate EViews to access various econometric estimators. To begin any estimation, you typically start by creating a new equation object. You'll find this option under the Object menu, where you select New Object and then Equation. Once an equation object is open, you define your model and choose the appropriate estimation method from the drop-down menu. As we've discussed, options like two-stage least squares, or TSLS, and Generalized Method of Moments, or GMM, are available for addressing endogeneity. For quick reference, the menu breadcrumbs on the right provide common navigation paths for estimation, diagnostics, and testing. For instance, to estimate an equation, you can use Quick Estimate Equation, and for checking your IV diagnostics, you would go to View IV Diagnostics. This slide provides a visual guide on how to set up the equation for estimation in EViews, specifically for our instrumental variables and GMM framework. In the equation specification field, we define our dependent variable, log PAC-PC, which represents cigarette consumption, along with our regressors, the constant C, the potentially endogenous price variable, log RAV-PRC, and the exogenous income variable, log per income. Now, pay close attention to the instrument list. A critical alert highlights that we must include all exogenous regressors from our equation in this list, as they effectively serve as their own instruments. Therefore, log per income and the constant C are listed alongside our primary instruments, the sales taxes R-taxo and R-tax. Failing to include exogenous regressors here would lead to an incorrectly specified model. Finally, we select GMM, Generalized Method of Moments, as our estimation method, and specify HAC, Newey-West, for the weighting matrix, aligning with our discussion on robust inference for heteroskedasticity and autocorrelation. This slide illustrates the key options when performing Generalized Method of Moments, or GMM, estimation within EViews. We see the Equation Estimation dialog, where we specify our model and instruments. Crucially, under the Estimation Weighting Matrix option, we've selected HAC, Newey-West. This choice is vital because it explicitly corrects for both heteroskedasticity and autocorrelation in the error terms. As a best practice, particularly when working with time series data such as GDP or inflation, it is always recommended to employ HAC consistent standard errors. This ensures that our standard errors are robust and our inferences about the significance of coefficients are valid, even if our model's errors exhibit serial correlation or non-constant variance. By selecting this option, we ensure the efficiency and reliability of our GMM estimates. Let's apply the instrumental variable concepts we've discussed to a classic case study from Stock and Watson, analyzing cigarette demand. Our primary goal is to accurately estimate the price elasticity of demand for cigarettes. Here, our dependent variable, y, is the log of packs per capita, representing demand. The crucial variable we're interested in, the log of real price, is considered endogenous. This is because unobserved factors, like public health campaigns or other tastes and preferences, could influence both cigarette consumption and policies affecting their price, creating a correlation with the error term. To address this endogeneity, we introduce sales taxes as our instrumental variables, z. The logic is straightforward. Sales taxes are determined by governments and directly influence the final price consumers pay for cigarettes. Critically, these taxes are assumed not to directly affect a consumer's underlying preference or desire for smoking, only the price they face. This makes sales taxes both relevant, as they impact price, and exogenous, as they are uncorrelated with unobserved factors affecting demand, thereby serving as valid instruments for price. Here are the results from our two-stage least squares, or TSLS, estimation for cigarette demand. Our dependent variable is the log of packs per capita. We are primarily interested in the coefficient for the endogenous variable, which is the log of the real average price of cigarettes. The estimated coefficient for price is negative 1.28. This value represents the estimated price elasticity of demand. Its interpretation is straightforward. A 1% increase in the real price of cigarettes leads to a 1.28% decrease in the quantity of cigarettes consumed per capita. The negative sign of this elasticity is consistent with the fundamental law of demand, making strong economic sense. These results provide our initial estimates, but they rely on the assumption of homoskedastic errors. Next, we will re-estimate the model using GMM to check for the robustness of these findings. Now we present the GMM estimation results, which utilize a hack-consistent weighting matrix, specifically the Newey-West method. This makes our standard errors robust to both heteroskedasticity and autocorrelation. You'll observe that the point estimates for the coefficients, such as negative 1.28 for the price elasticity, are identical to what we found with TSLS. This is entirely expected, as GMM provides the same consistent estimates, but with potentially different standard errors. The crucial difference lies in those standard errors. For example, compare the standard error for log RAVPRC here, which is 0.22, to the 0.15 we obtain from the TSLS estimation. The larger GMM standard errors indicate that heteroskedasticity or serial correlation was indeed present in the data. This means that our earlier TSLS results, which assumed homoskedastic errors, were likely overly optimistic, leading to smaller standard errors and potentially misleading significance levels. The GMM estimation, therefore, provides more reliable and robust inference. In the next step, we will use the J statistic from this GMM output to perform an over-identification test. The J statistic is a crucial diagnostic tool used for an over-identification test, which is only feasible when you have more instruments than endogenous variables in your model. In our case, we have two instruments for one endogenous variable, meaning the model is over-identified. This test assesses the validity of our instruments, specifically checking if they are uncorrelated with the error term. The null hypothesis, H0, states that all instruments are valid. Our decision rule for this test is to examine the p-value, or prob of J statistic. If this probability is greater than 0.05, we do not reject the null hypothesis, concluding that our instruments are indeed valid. Looking at the results, the J statistic is 1.845, and its corresponding p-value is 0.3975. Since 0.3975 is significantly larger than 0.05, we confidently do not reject the null hypothesis, affirming that our chosen instruments are valid for this model. After confirming the validity of our instruments with the J statistic, the next crucial diagnostic is to check for instrument strength. Weak instruments, which are only weakly correlated with the endogenous regressor, can lead to biased instrumental variable estimates. We assess this using the Krag-Donald F statistic, derived from the first-stage regression. A common rule of thumb, proposed by Stock and Watson, suggests that a first-stage F statistic greater than 10 indicates sufficiently strong instruments. More formally, we compare it against stock Yogo critical values. Our calculated F statistic is 45.2, which is substantially larger than the critical value of 16.38 for a 10% maximal IV bias. This clear margin, 45.2 being much greater than 16.38, confirms that our instruments are strong. This is crucial. If they were weak, our estimates would be unreliable. With both validity and strength confirmed, we can now proceed to our final diagnostic, which addresses whether an IV approach was even necessary. Our final diagnostic is the Durbin-Wu-Hausmann test, a crucial step to formally determine if our regressor is truly endogenous. This test is vital because instrumental variable, or IV, estimators, while consistent in the presence of endogeneity, are less efficient than ordinary least squares. In simpler terms, IV estimates typically have larger standard errors, so we only want to use them if it's absolutely necessary. The null hypothesis for this test is that the regressor is exogenous, implying that OLS would be a consistent and preferred estimator. Conversely, the alternative hypothesis is that the regressor is endogenous. Looking at our results, the Durbin-Wu-Hausmann F statistic yields a probability value of 0.0032. Since this p-value is well below our significance level of 0.05, we confidently reject the null hypothesis. This strong statistical evidence confirms that our price variable is indeed endogenous, underscoring the necessity of using instrumental variable techniques for consistent and reliable estimation in our cigarette demand model. To wrap up our discussion on instrumental variables and GMM, let's review the best practices for effectively tackling endogeneity. First, always start with a solid theoretical foundation. You need a strong economic or theoretical justification for why endogeneity exists in your model, such as feedback loops or omitted variables. Second, the choice of instruments is absolutely critical. You must select instruments that are both relevant, meaning they are correlated with your endogenous regressor, and exogenous, meaning they are uncorrelated with the error term. This is where the garbage in, garbage out principle truly applies. No advanced GMM technique can fix a fundamentally flawed instrument. The quality of your instrument is far more important than the specific weighting matrix you choose. Third, regarding estimation, a practical approach